In this section, I'm going to talk about a couple of things, a couple of properties that are influenced by the energies that I discussed earlier. One is atomic size. How big are atoms? And actually, the atomic size is somewhat counterintuitive. The atomic radius, or the overall size of each atom, becomes smaller as I increase atomic number across one row of the periodic table. This is unexpected. You think, why shouldn't heavier atoms be smaller? Atoms that have more electrons, why shouldn't heavier atoms be larger, rather? Have more electrons, more protons in the nucleus, shouldn't the atom be larger? But actually, as I add electrons and protons to an atom, within one row of the periodic table, the atoms become smaller. And this has to do with the increasing charge of the nucleus. As I showed with the atomic energy levels, orbital energy levels, the outer shell becomes more tightly bound, lower energy, and hence smaller as I go across a row of the periodic table. And as I go across the row, I keep putting atoms into that same shell, and so that shell is becoming smaller. However, there's a large jump in atomic size as I go from one row of the periodic table to the next. That's because the extra electron that I'm adding is going in. Here you can see atomic sizes into the higher shell. Rows of the periodic table. Notice lithium here, 0.134, a large atom comparatively, and I go down, and when I get to neon, only 0.69, and the unit there is angstroms, and this is the radius of the atom. And then notice that when I go from neon to the next element, sodium, there's a large jump in atomic size, and then I go down as I go across a row. Of course, as I go down a column of the periodic table, the atomic sizes go up because there's more and more shells occupied. The other thing, the other property is ionization energies. What is ionization energy? Ionization energy is the energy change for removing an electron from a neutral atom. So I can think of any atom in the periodic table, I put it into the gas phase, and I remove an electron, maybe with a photon or something like that. How much energy does it take to remove that electron? And that energy is roughly equal to the negative of the energy of the highest occupied orbital. Remember, 0 on the energy scale represents removing an electron. So I have some negative energy of the highest orbital. I have some energy of the highest orbital. It's a negative number. I have to add that much energy to remove the electron. So the more negative that orbital is, the higher the ionization energy. So therefore, as I go across the row of the periodic table, as the highest orbital becomes smaller and lower in energy, and that energy is negative, the ionization energy is going up as atomic size is going down. And then, of course, there's a sharp drop in ionization energy when I start a new row. And again, this is related to, this is kind of the same effect as the atom becoming bigger. As the atom becomes bigger, it takes less energy to remove the electron. That sharp drop is due to putting the new electron into a new shell. We can explain this in terms of the Z effect of the effective nuclear charge for the outer electrons. Remember, for one electron outside a filled shell in a neutral atom, the core is a +1 charge, and that's the effective charge that's seen by the outer electron, and that's why that outer electron. This is the much familiar graph that shows ionization energies as a function of atomic number. And so I can see as I go across a row, hydrogen, the first row, 2 elements, hydrogen here, Helium is much higher, and then I go to the next row, and there's a large drop in ionization energy. It's very easy to remove the valence electron from lithium. And then there's a general trend upward as I go from lithium up to neon, and then again another large drop as I go to the beginning of the next row. There's some glitches in here, and I won't go into those in details, but you could, if you think about it, you can see that those have to do with forming with electrons going into new subshells. And the glitch here having to do with a half-filled subshell. But we won't go into in detail. We'll just consider beginning of a row, going up to the end of the row, and then a drop. This series here is where we start in the transition metals, and we go up to krypton, a noble gas, and notice that all of the noble gases occur where I have just filled p subshell. And then I go to a new row. This is the next D block. This represents the next D block of the periodic table, and I reach the next noble gas. Large drop to cesium. This is where this region in here is where I'm filling in the F block. That's the part of the periodic table, the two rows below. That's the so-called intertransition elements, or the F block.